guys. What we are going to do now is a practical case using the airline data, that is the number of international airline passengers all over the world. This data set is called Airline/EN GDT. As always, you can download it from the virtual campus. If we choose the time series and right-click and generate a time series plot, we see this very familiar profile. We have a trending time series, meaning that its level increases over the time. So this time series is non-stationary because it has trend. It is also non-stationary in the mean because of a different reason. It is seasonal. Seasonality is a different type of non-stationarity. It means that the level of the time series changes and changes again over an annual seasonal cycle. The peaks of this seasonal cycle occur during summer, and the valleys, the lows of the seasonal cycle during winter. A third feature of this time series is that its variability increases with the level of the time series. Note that I have said variability. I didn't use the word variance. I didn't say variance because for the variance to be defined, the mean should be stable. This is the reason what I spoken about variability. I could also speak about dispersion. I could speak about everything, but speaking about variance is not proper in this case. So this will be the first issue that we will address to stabilize the variability of the time series. As you know, by the theory lessons, you can do this by logging the data. So you have here a time series plot showing the log of the previous time series. In this case, you see that the variability is more or less stable, that the time series continues displaying a trend in behavior and continues displaying seasonality. But at least we stabilize the variability. So this airline variable will be the endogenous variable for all the models that we are going to fit. So let's try first to capture the level of the time series. We can try to do this by using the variable time as explanatory variable. As you see, time is equal to 1, 2, 3, 4 for the first, second, third, and fourth observations, and so on. So if we run our ordinary least squares regression of log airline against time, you will get this equation. To see graphically the result, you can choose graphs fitted actual plot against time. Here you will visualize what we are doing. We are fitting a straight line that crosses in the least squares path the time series that we have observed. If you see, the fitting seems a bit changing. It is crossing more or less the center of the annual cycle. In this case, it is close to the peak of the annual cycle at the beginning of the sample. We can see this behavior more clearly in the residuals. Graphs residual plot against time. As you can see, the residuals seem to describe a certain curve. They are seasonally, of course, because we haven't done anything with seasonality, but they display some type of nonlinear behavior. To capture this nonlinearity, we can improve the model by editing it and adding this variable sqtime. Sqtime is just the variable time but squared, raised to the second power. So what we will do is, instead of fitting a straight line like in model 1, we will be fitting a polynomial in which log airline is a function of a constant term, time, and time squared. If we plot again the fitted actual plot against time, we will see that the shape of this regression function is a curve. And if we plot the residuals against time, we will see that they look more stable. They do not display a clear nonlinear behavior as in the previous case. So we improved the model. We improved the model for the trend of the time series, for the changes in the level. We can continue improving it by adding variables able to capture this seasonal behavior in the residuals. So let's close model 1. Let's take model 2 and let's improve it by editing, modifying the model. I will now try to add these 12 dummy variables at the same time. dm1 is defined as equal to 1 if we are in January and 0 otherwise. dm2 the same for February, dm12 the same from December, for December. If you click OK, you will see that you haven't been able to estimate exactly this model. Look at this message. Omitted due to exact collinearity dm12. And you see that you are only taking into account dm1 to dm11. What Gretel have done is detecting a case of exact collinearity. Why? Because underlying the constant term, there is a variable which is a vector of ones. And if you add dm1, dm2 up to dm12, you will also get a vector of ones. And this is collinearity. One variable in the model is an exact linear combination of other 12 variables in this case. The choice of the variable to be omitted, in this case Gretel have done the job for us, is arbitrary. It only changes the baseline level of the variable. Okay, to illustrate this, let's modify model 3. In this case, we are going to suppress dm1, that is January, and we will add dm12. So we are suppressing January instead of December. I click OK and get an equivalent model. How do I know that this model is equivalent to the previous one? Because I have exactly the same R squared. So both of them are describing the sample in exactly the same way. What is the difference between both? The difference is in the baseline value. Note that if I am in January, these 12 variables will be equal to 0 because they correspond to other months. So the model for the trend, in this case, will provide us for the expected level for the value of log airline in January. If instead of January I am in February, I have here dm2. dm2 tells me that the level of the time series will be the baseline level, that is January, minus 2% approx. If I am in March, the level will be the level expected for January minus 11% approach. So these coefficients here describe the seasonal pattern. You can see that from June to September, you are in the seasonal peak, meaning that international airline flights for persons are more frequent during the warm months, probably due to holiday or to leisure trips, than in the cold months. And the R squared is slightly larger than that in previous models. This model describes more of the time series. If we plot the fitted versus actual plot over time, we see that the fitted blue line is getting closer to the actual red line. Okay, but this model is not perfect. If we test for autocorrelation in the residuals, for example, let's allow not 12, but 3 lags, we will obtain the Boyce-Godfrey test for autocorrelation that we studied in theory. The regression, the auxiliary regression, has an endogenous variable u hat. The explanatory variables are those in the model. And I also have 3 lags of the residuals. The unadjusted R squared is very large. What we have here is 3 different tests, statistic, for autocorrelation of the errors. In the first 2 cases, I am testing the null that all these coefficients, the regression coefficients, are 0 at the same time. This will only happen if u hat is independent both on the original model regressors and on the first, second, and third lag of the residual. As you can see, the null is rejected clearly. The third test is a direct test for autocorrelation of the residuals that we haven't seen in theory. So you see that you have autocorrelated errors. The test statistic of Boyce-Godfrey n times the R squared is very large, and the p-value is accordingly very small. So we could improve the model. We could improve the model by adding to the relationship model, that is this equation, the equation which relates the regressors with the endogenous variable, we could improve it by adding to it a second equation, a model for the error. A model for the error telling us that the current error in the relation model would be a function of its first order lag, so the error at t minus 1, plus a non-autocorrelated error, which would be the final error for the model. To do this, we can use another different function of Gretel. I will close all these windows, which is in the univariate time series menu, is AR errors. AR errors, GLS, is a way to add to the baseline regression an autoregressive error model. An autoregressive error model is the one which relates the error at time t with the errors at time t minus 1, t minus 2, and so on. So we identified an autoregressive of first order error. You click OK, and what you have here is this new and enhanced model. Now you are iterating. To iterate in a regression framework means that you are estimating one model by least squares, you adjust for autocorrelation, a second model, you adjust again for autocorrelation, a third model, and a fourth model. And then you stop iterating. You stopped iterating because this row parameter, which is the coefficient related epsilon t minus 1 with epsilon t, didn't change in these 3 iterations, and the sum of a squared residual didn't change too. So we got to a stable solution. Stable solution with this row coefficient. This would mean that the residual at time t is 0.67 times the residual at time t minus 1 plus an uncorrelated error. And this would be the model for the errors of this equation. In this equation, you see that you have most of the coefficients significant. In previous regressions, some of them, many of them, were non-significant. Why do this happen? This happens because in previous equations, we were estimating with autocorrelated errors, and this invalidated the standard test resulting from the standard theory of econometrics. And that is all that I wanted to show you today. As always, I wish you good night and good luck. Thank you so much.